All right, so Physical Science 20, we're going to take a look at Chapter 14, Section 5 here. We're going to talk about equations for curved mirrors. This is going to come up again in equations for lenses, which will come up in the next chapter, I believe. But this is your first indication as to how we can find the distance of the image mathematically. So we've been doing ray diagrams, but now we're going to look at how to do it mathematically. So I've drawn a little diagram over here with a principal axis, center of curvature, the focus, and an object and an image here. Okay, so normally we've been drawing lines, rays, that go through these points, and that's how we're going to find the image. But what we're going to do is we're going to look at the math, how to do that. So ray diagrams are useful for figuring out where an image will appear, but you do not always want to have to draw a picture. And you don't always want to have to get your ruler out to measure things. And so there is a predictable mathematical way to look at this. So it's called the mirror equation, and here's the mirror equation right down here. It's 1 over the distance of the object, so that's the reciprocal of the distance of the object, plus 1 over the distance of the image will always equal 1 over the focal length. So remember, f, the focal length, is this distance right here. This is f, from here to there. Okay, you see that? And, of course, this right here is the distance of the object, dO. And that's always to the mirror, right? To the center, where the center of the mirror would be. Even if it's curved, it's always kind of to the center, the vertical line that would represent the mirror. And then, of course, the distance of the image would be the distance from, the image here to the mirror as well. So that's di. So those are your three lengths, and they all happen to be related by this math equation. So what's handy about this is if you're given two of these, you can always solve for the third one. Usually you'll be given the focal length and then the distance of the object, right? Because you can calculate the distance of the object, so you can find the distance of the image. From there, we can find other things like height and things like that, because there are other relationships there. So you have to make sure that in order for this to work properly, that you're using the correct signs, okay? So there is something called sign convention, and I will just erase some of this stuff so I can go over this with you. So let's go over the rules for the sign convention. So all distances are measured from the vertex of the curved mirror. So that's this V point right here, right, where the principal axis contacts the mirror. So all distances are measured from here and then out to either the object or the image. Distances of real objects, okay, so now you want to remember what real objects are. Real objects would be objects that are in front of the mirror or that can be projected onto a screen, right, so images that form in front. Distances would be, real objects would be positive. So this right here, if this was, let's say this was the image right here, this distance would be positive. Distances of virtual objects are negative. So anything that's behind the mirror this way is negative. So behind the mirror going back this way, those would be negative. So distances in front of the mirror are positive, behind the mirror are negative. Also, the last thing you kind of want to remember here, object heights and image heights are positive when measured upward. So if we're measuring a height like this right here, up from the principal axis or in a vertical upright position, those are always positive. And then in the negative, okay, it's a negative when it's measured down. So over here, the height of this right here, whether it's an object or an image, would be negative because it's facing downward. Okay, and yeah, we usually have to do a direction so that all of the signs match up in our equations. Okay, so if we get these signs right, that'll help us. When you do the math, if it's a negative distance, let's say, you know that it's a virtual image, and if it's a negative height, you know that the image is upside down. Okay, so the signs are important. Okay, recall the magnification of an image is given by this equation. Now, this equation right here is the magnification equation. And now that we are paying close attention to our signs, this is something that we have to make sure. HI, that's the height of the image, divided by the height of the object, this ratio, is equal to negative di over do. All right? So you have to make sure you have this negative sign in here now. So the magnification equation becomes HI over HO equals negative di over do. And that will ensure that all of the signs are correct. Any questions? All right, so here's a sample problem we're going to do. It's actually in your textbook, page 447. But it says this: an object is 30 centimeters away from a converging mirror. Okay, so we know a couple things already. We know that the mirror is converging, so it's kind of bending in towards us at the edges, right? And all the light rays would bounce off the mirror and come towards the focus, through the focus. Now, in diagrams, often they'll use a straight line here to measure from, and then just curve the tops and the edges. Okay, so this is a converging mirror, and the object is 30 centimeters away. So the diagram, which you don't have to draw, is oftentimes it's helpful so that you have an idea of what your answer should be using what you know from the ray diagrams. But you don't have to sketch it. I'm just going to do it here just so we can see that it lines up. The math lines up with the ray diagrams we've been doing. So we've got about 30 centimeters here. Let's see. The radius of curvature is 10. So the radius of curvature, do you know what that refers to? The radius of curvature? What would that refer to on this diagram over here? Yeah, the value for C. So this right here is 10. So right here, 10. Okay? Yeah, it's very good. At what distance from the mirror will the image be formed? Okay, so let's take a look at what we have. And I think this is coming later, so I should erase that. What do we have so far? Well, we have an object is 30 centimeters away from the mirror. So that is the distance of what? The object, right? So we have DO. We have this. That's great. I want to find DI. You see, this is unknown. That's what the question A asked for. And focal length. I don't see focal length anywhere, but how can I get focal length from what I'm given? Do you see how I can get this distance here? How do I get that from what I'm given? I'm given this number and this number. Do you remember the relationship between the focal length and the radius of curvature? The C and the F there? The C is twice the distance of F. So F is half of the length of C. Yeah. So F here is 5 centimeters. Okay, it's half of 10. Oh yeah, that's always, yeah, that relationship always holds true, absolutely. Yeah, if you're given F, you know that C is twice that. If you're given C, you know that F is half of that. All right, so what do we have? We have 1 over 30 plus 1 over, I don't know what DI is, so I'll leave it as DI, equals 1 over 5. Okay, you with me there so far? All right, now you have to be real careful here. We do want to get DI all by itself, so let's leave this term that has DI in it on the left side. And that what that means is we have to subtract 1 over 30 from both sides. Does that make sense? Now, well, we have to subtract 1 over 30 from both sides of the equation so I can get rid of it over here. Now, what you want to be careful not to do is don't go 5 minus 30. Don't say that's negative 25. Remember, you can't do that. The math here says that we have to have a common denominator. So I'm actually going to multiply the top and the bottom here by 6 so I can get a 30. You see that? Okay, common denominator is very important. So 1 over DI, this actually is changed to now 6 over 30. Whoops, not 6 over 60. 6 over 30. Does that make sense? Minus 1 over 30. Why do you keep the negative? Well, this is 1/5 minus 1 over 30. So I just need to change this 1/5 into a fraction with a denominator of 30. That's just all I'm doing in this step. So now when I combine these, what do I get now when I'm now able to subtract these? So 1 over di equals what? 5? 5 over 30, yes.
Oh, so the bottom just stays the same?
The bottom stays the same, yeah. Yeah, when you're subtracting fractions, if you have a common denominator, you can simply subtract the tops, but leave the denominator. Yeah, that's the rules there. All right, now I want you to see something. If you have 1 over di equals 5 over 30, you can actually take the reciprocal of both sides. And so di over 1 is the same as 30 over 5. You see how I just flipped the fractions on both sides? That's totally okay to do. So now I have di equals 30 over 5, and of course 30 over 5 simplifies to 6. And that's 6 centimeters. That's the distance of the image. Now here's 5 right here, the focal length. So 6 is going to be right about here. You see that? I don't know if you can see that actually. A big fat head in the way. So 6 is going to be right about here. So the object, or the image, sorry, is going to be located about here on the principal axis. We don't know if it goes up or down yet. We don't know that yet. That's what B is telling us. So if the object is 4 centimeters tall, how tall is the image? Okay. So now we know that this here is 4 centimeters tall. It's positive 4 centimeters because it's facing upward. And so I have to use what I know, and I know DO, DI, and F now. And I have to use what I know to find the height of the image. So this is where we use our magnification equation. This one right here for B. Okay? Because I know the distance of the object. And I know the distance of the image now because we just calculated it over here. I know the height of the object because it's given, so guess what? I only have one thing left now to solve for, and that's the height of the image. Okay? So let's give it a try. So height of image we don't know. Let's just leave that as HI. HO is 4 centimeters. Equals negative. Now, negative what? Well, DI is 6, so let's just put a 6 in there. So you see how that positive 6 becomes a negative 6 because of this negative sign? And the distance of the object we said was what? 30 centimeters? So are you seeing how I'm filling this equation out here? Okay, so if I want to get rid of that 4, I multiply both sides by 4 because that will in effect get rid of the 4 over here. So I'm just left with HI equals, now what's negative 6 times 4 is negative what, 24 over 30. Come on now, there we go. Alright, because that 4 is like a 4 over 1. Okay, does that look good? And so 24 over 30 is going to be simplified to what? Negative, actually it's a negative 4/5. So the height of the image, HI, is negative 4/5. So negative means that it is facing downward, right? Negative height. So negative height. And 4/5 is about 0.8 centimeters. All right. As long as I've done everything correct here, I think we should be good. So 6 there.
Should it be negative?
Yeah, it's negative, yeah. Yeah, you're right, negative, yeah, so let's write that. So negative 0.8 centimeters is the height of the image. Okay, so there's your problem. That's your sample problem. Now that'll help you do the assignment there, which is on page 448 in your physics textbook there. Okay, any questions? So remember, 1 over DO plus 1 over DI equals 1 over F. And also the magnification equation, which is HI over HO equals negative DI over DO. You remember those two, and you can solve for the heights and distances of the images and object.